I don't think so. So it's live now. Hello, internet. Let me go close this door real quick. See, this one's fine.
Good.
Yeah.
Well, welcome everybody. We're going to get started here. I'm one of Matt's committee members. My name's Dan Levitt. I've known Matt Acre about 10 years. And one of the first interactions we ever had was spring semester 10 years ago, herpetology class. Matt was an undergraduate. I was a graduate student at the time. And the professor had us, audit the herpetology class. And Matt was giving a presentation for, one of those 5-minute senior project presentations. I believe it was ant eating and amphibians.
Yep.
And Matt stood up and the title slide said ant eating and amphibians. And Matt proceeded to talk at length about ant eating and lizards. For you herpetologists out there, you know that lizards are not amphibians. So later on, Matt and I were talking, and he's like, "So how do you think I did?" I said, "Well, don't ever do that again."
Worst presentation I ever gave.
Well, and Matt's gone on. He's done a lot since then. In 2017, he got the Texas chapter of AFS Best Student Presentation. So something was learned, I suppose.
Yeah.
He also got top 5 from the Joint Meeting of Ichthyologists and Herpetologists meeting. And then in 2018, he got honorable mention for Best Student Presentation by the American Fisheries Society. He's been awarded a number of different awards. The Texas chapter has given him the Harry Tennyson Scholarship, the Clark Hubbs Award, and the Texas chapter for Outstanding Fisheries Student of the Year. So some pretty big accolades there. The university named him the Warren B. Ballard Memorial Award winner. And also from the Southern Division of the American Fisheries Society, he won the Jimmy Pigg Award, Memorial Award. Some pretty big accomplishments. Not all of us would be able to have all of those at his age. In addition to that, Matt has 5 peer-reviewed publications, and we're expecting much, much more out of him. I'll turn the floor over to Matt for his dissertation defense on the blue sucker, and I'll allow you
Thanks,
to introduce your presentation.
Appreciate it. Yeah, a lot, Dan. Thank you to committee members for being here, and Dr. Kevin Mulligan for being the Dean's representative here today. Buenos gracias por estar aquí. So I want to start out by talking about some historical context before I jump into the details of blue sucker population and habitat use and migratory responses to flow regime. And I think a good place to start is with fish harvests and river alterations over 200 years. So, prior to mass European settlement in the 1800s, there was quite a bit of evidence to suggest that fisheries harvest was relatively sustainable and essentially sustenance-based, right? But with mass immigration of European settlers to North America, you get an increase in fishing technology and technology in general. And this eventually leads to commercial fisheries that we know today here in the United States. Just one example from a small section of the Mississippi River. So there's this report done in the 1930s by Coker, and in it they're talking about sucker harvest, and they even include blue sucker. And so what I want you to notice here is that in the late 1800s, 1894 to be exact, there's about 2.2 million pounds of sucker being harvested annually from this small section of the Mississippi River. By 1922, there's about 700,000 pounds. And this is in due part to alterations of riverine systems, but also overharvest. This is a 300% decrease in catch. And even more interesting, Coker notes blue sucker in here. He notes it as a valuable food fish. And he even talks about artificial propagation programs or captive propagation programs. Most of the people in this room have probably never even heard of blue sucker, unless of course you've heard me droning on about it for the last 3 or 4 years. So this is kind of interesting that we're thinking about captive propagation programs for this non-sport fish, but a commercially harvested fish back in the 1930s. So kind of simultaneously, there's also river alterations occurring, dam construction. And this photograph here is the site of current day Tom Miller Dam in the lower Colorado River, the river that runs through Austin, Texas. And here they are laying the last key in 1992. However, in 1900, there's a big flood that comes through and washes it out. Austinites, they rebuild it. It washes out again in 1913. And then a big flood comes through in 1935 and washes it out again. And this is more or less the camel that breaks the straw that breaks the camel's back, right? This is when Austinites are starting to get pretty frustrated with the inundation of property and the loss of property. It's really expensive to rebuild after a big flood like this. And this is kind of happening across the country too, simultaneously. So what I want you to notice is that by 1885, there's 4 railroads that are connecting the east to the west. And that's the time you're going to see dams being constructed out there in the west. So each one of these black dots is a dam. By 1914, we have production needs for World War I. By 1944, we have a 100% production increase for war efforts. And then right around the 1960s or 70s, coming up here in just a second, is the age of dams. This is when dam construction explodes in the United States. And these are just dams that are 50 foot in height or greater. So these are major reservoirs. Around the 1990s, 2000s, dam construction decreases pretty seriously. And this is in part due to that dams have, right? So think about fish that are known as fluvial specialists, right? These are fish that need riverine conditions to complete their life cycle. Fish like alligator gar and salmonids and white bass, trout and ictalurids, your minnows, cyprinids, catastomids, as well as sturgeon. And this last group here, these catastomids, this includes the blue sucker, the fish I want to talk about today. So this fish is thought to be, or is known to be, a potamodromous fish. That means it makes strictly freshwater migrations. And they're thought to be relatively predictable. These cyclical events where they move upstream to spawning grounds, and then they make these turns. It's with certain cues. Unfortunately, the obvious implications of a dam is that they no longer can reach those spawning grounds. The other is that spawning grounds become inundated. But the one that people often think of much less is the alteration to the hydrology downstream. And there are 4 major ways that a dam can alter the hydrology of a river. Right? It can change the magnitude and the frequency of particular flow. It can change the rate of change, or how flashy the system is. So think of like your backyard creek, which is a flashy system, versus the Mississippi River, not very flashy. It can also change the timing of particular flows, as well as the duration. Because each one of these flood events right here have implications for different species depending on the timing and the duration and the magnitude. And so this is why we consider blue sucker, which is and it's also relatively well distributed. It was known to occur in 20 states. Okay, so all of these states here that are this tannish color. It was extirpated, or it's extirpated from Pennsylvania. And so you might think that this is great, really well distributed. But when you start to look at the listing state by state, in 19 of the 22 states are listed in some way. So it's either a species of greatest conservation concern, it's threatened, or it's endangered by the state. Regardless of all these states, there is no federal. And the listing becomes a little bit more precarious when you start to look at it within the state of Texas. So these 3 rivers right here, the blue sucker is suspect. There were some observations back in the late 50s, early 60s, but there are no vouchered specimens. The Rio Grande is a completely different species, split in 1999 by Burn Maiden. Drainages where they occur currently. And within the lower Colorado River, they actually do not above what is known as the Highland Dams, or the Highland Lakes, rather. It's a series of dams. And so those dams altered the hydrology downstream pretty significantly. So you're looking at the hydrograph at Austin. And what I want to point out is in 1937, which is indicated by this dashed line, Buchanan Dam was constructed. By 1940 is that dashed dotted line, that's Mansfield Dam. And those 3 floods that I showed you earlier that wiped out those, the Tom Miller Dam, that's these 3 right here. So the lower Colorado River has not experienced magnitude of flood, anything like that, since about 1940. And the duration of those floods has drastically been reduced. And that has implications for a fish that is thought to be queued up by certain flow events, right? The blue sucker. And this fish, you can understand whenever you look at how big this fish is, why it was commercially harvested. 100 millimeters, years of age or so. It's a really big, beautiful, charismatic fish. And it's thought that they make these spawning runs in very specific time, between February and May, in some cases upwards of 200 kilometers, though this is likely underestimated. And they make these runs to very specific habitat, to these like riffle run habitats with big boulders and cobble and faster flowing water. And as I stated before, it's long been assumed, there's not a whole lot of actual evidence to suggest that these migrations are queued up by temperature and flow. And they're currently experiencing this reduction or extirpation throughout their entire range, right? And the population within the lower Colorado River has thought they've been in trouble for quite some time. And study. So that kind of leads me into the objectives of why we started this whole thing to begin with. So we were tasked with identifying the demographics and the probability of persistence of this population into the future, the habitat use and selection of the species, and the abiotic drivers that might be making these fish move, which includes spawning migrations. So we're going to go into our first objective here, which is the demographics and the probability of persistence into the future. Specifically, I want to investigate the annual survival and the mortality of the fish, estimate the population size and the annual recruitment, as well as the probability of persistence, okay? So, as I've stated, we're in the lower Colorado River. Specifically, we're looking at this location between Austin and Altair, or river kilometer 460 and river kilometer 163. So when I say river kilometer, it just means a location within the river, right? So river kilometer 0 would be Matagorda Bay. It increases in the upstream direction. So at Austin, there's a dam called Longhorn Dam. So this is impassable throughout the entire year. At Altair, there's a low-head riprap dam that can be passed by fish under certain flow conditions, but makes a pretty good bookend for our study. And within the lower Colorado River, I wanted to identify all of the riffles, because recall, we think that bluesucker are relatively well associated with these types of habitats. So you're looking at every single riffle as identified with a GPS location throughout the river. And I should probably explain what a riffle is a little bit better so we get an idea of what that means. So you're looking at the aerial view of a river on top and the profile view here on the bottom. So the riffle is that area with generally faster flowing water. It's pretty narrow in terms of the morphology of the river. This is the area that people call whitewater because the top of the water is like turning over. As that river opens up into a run, the river starts to speed up a little bit, but now you have laminar flow. The surface of the water is no longer broken. And it's these two locations where we think bluesucker hang out the most. As that run opens up even more, it opens up into a pool. This is where you have really slow flowing water. And then as the channel starts to narrow again, you go right back into a riffle. So this is pretty normal for the lower Colorado River. This is not necessarily how every river works, but in our system it does. So that's what you're looking at here. It's every single riffle identified with a GPS mark. But I needed to select 30 of these sites to go out and mark and recapture, so we just randomly selected, and these are going to be the locations where we attempt to go out and capture and recapture bluesucker. Whenever we do this, I go out with a boat electrofisher, so it's kind of a standard technique for a fisheries world. We send electricity through the water, and we attempt to shock up bluesucker, as you see here in the bottom photo. Each site was shocked for 1,800 seconds. When a fish was captured, we brought it into the boat, and there were a few other things we did here, and that is we took a fin ray clip. So we took the left pectoral fin ray. You're looking at a fresh clip here on this top in that red box, and this is what it looks like about 4 to 6 months after it's been recovered. So we take those fin ray clips, and we also inject each one of these fish with a passive integrated transponder. Okay, so the fin rays are really interesting. This is where so we can use those opaque zones or those dark zones to essentially estimate the age of the fish. And so you can see here on the bottom, you've got a 4-year-old, and on the bottom, something like a 25-year-old or so. So with these fin rays now, and the data from the age estimates from the fin rays, we can estimate the age, annual mortality, survival, as well as annual recruitment from the estimated ages. From the marker capture, we're going to estimate the population size, and then we're going to take all this data and we're going to put it into a population viability analysis, or a PVA. And so we're going to fill this chart out together. We're going to fill out the population size, or the estimated population size, the estimated cohort strength by year, the per capita birth rate, the death rate, as well as lambda, which is the rate of change in the population annually. So we need to start here at the population size. So I went out a total of 6 times to mark recapture these fish in July, September, and November of 2016, and then in May, July, and September of 2017. I captured 167 fish, 15 of which were recaptures. Unfortunately, 10 of them were in the very last event. So we couldn't do a whole lot in terms of with mark other than get a rough estimate of population size, which was roughly 679 fish, with a lower boundary of 449, upper boundary of about 1,089 fish or so. So we're dealing with a relatively small population, considering this fish used to be commercially harvested. So we have population size, all right? We need to get the cohort strength by year, or what is known as recruitment. So this is when a fish is a reproductive member of the population, how we're going to define recruitment. And so these are the estimated ages on the x-axis, and the frequency or the count on the y. And what I want to point out here is that there's relatively constant recruitment for the most part, but the majority of the fish fall within like 7 to 17 years old or so. And the concerning part is that there are only a few individuals, maybe like, I don't know, 15 or so, that make up those younger individuals. So between 3 and 6 is pretty rare in the system. And this will translate over whenever we attempt to estimate the annual recruitment. Okay, recall, because this is the most important part of the PVA. And so it seems to be that most years are relatively constant. There are a few years in the mid-90s or so that were not so great. And then it drops off pretty seriously here in 2009. We have our strongest year in 2004, about 428 individuals or so, and our weakest year in 2004, which is 0. Okay, so we have our estimated recruitment annually between 0 and 428. So getting the per capita birth rate is relatively simple. We just take the estimated cohort strength divided by the population estimate. So now we can get this annually. Death rate is a little bit more complicated. So I showed you this graph already. This is the estimated age and the frequency. So there's a method that Ricker developed in 1975 that would say that to estimate the annual mortality, to get at the death rate, I would need to use the age class 12 and beyond to estimate annual mortality by regressing this line. But the problem with this is that Ricker assumes that anything younger than 12 is not susceptible to my gear type. The problem with that is that these individuals are 682 millimeters, which is a really big fish. And a lot of those fish that were younger were about the same size. So what I did was I allowed for any age class that was plus or minus a standard deviation within that size to be included in the model, right? So our new line ends up right here. We regress this. And this gives us annual mortality of 15%. That means that the annual survival is 85%. So from any given year to year, 85% of the population persists into the future. Okay, but remember, the important part of this is the annual mortality. That's this part right here, because we need to plug this into our death rate. So we have death rate now. Now getting lambda is relatively simple as well. This is just a math problem. We take E, which is the mathematical constant, raised to the birth rate divided by the death rate. Okay, so we're going to allow population size and the death rate constant through time, and the cohort strength and the birth rate, the per capita birth rate, is going to change by year. And we're going to group these. Recall that 2009 or so was about the time when recruitment was pretty low. So we're going to group these in that way. So, for example, the cohort 2008 to 2014 has a mean lambda or rate of change of 0.9 and a standard deviation of 0.04. And the way to interpret that standard deviation is like as stochasticity. So these are events that we can't necessarily plan for. For example, let me show you how it's going to work in the PVA setup. So let's take this top one, this cohort 2008 to 2014, for example. So what I'm going to allow happen each time step in the PVA, I'm going to allow the model to take a random lambda from a normal distribution of 0.9, or a mean of 0.9, and a standard deviation of 0.04. And the reason that's important in this model is because it means that getting a value greater than 1 is really unlikely. It's not impossible, but it's unlikely, right? And that means, and the reason that's important is because a lambda greater than 1 means the population is increasing. A value less than 1 means the population is decreasing. Okay, so for example, in time step 1, I pulled a lambda 0.95. And the next time step, same story, less than 1. Next time step, less than 1. It's in this next time step between 3 and 4 where I got lucky and I pulled a value greater than 1 and the population increases. So I allow this to randomly draw a value for 25 years. I iterate this 1,000 times and I want to look at the ending population because this is going to tell us whether or not the population persists. I set thresholds. So I chose for this talk 50 and 500. So that means that if the population makes it to 50 or greater, the population persists. If it makes it to 500 or greater, it persists. So I'm going to present both of the probabilities simultaneously. On the x-axis, you're going to have time, and on the y-axis, you're going to have the projected population size. So the first two cohorts that I want to present are the 1993 to 2008 growth trend, which had a mean lambda of 1.24 and a standard deviation of 0.21. So this is the first 50 iterations graphed here in each one of these graphs. And so in this scenario, the probability of persisting to 50 and 500 is both 100%. No problem, the population is going to make it. From 1993 to 2014, you got a mean lambda of 1.15, standard deviation of 0.24. You got a little bit more variation, some populations kind of bouncing up and down. But under this scenario, we also have a probability of persistence of 100 for both 50 and 500. It's not until we start to look at the most recent growth data, or excuse me, recruitment data, that we find a little bit of a problem. That's because in 2009 and 2014, if you'll recall, the mean lambda was 0.9 with standard deviation relatively small. There's only one way to go, and that's down. In this particular case, the probability of persistence to 50 is 34%, and to 500 is 0. So because that standard deviation was so small, in this last iteration, I decided to increase the standard deviation to 0.3. I wanted to allow a little bit more stochasticity within the model. And in this scenario, you can see that the population bounces several times, right? Some even get up to like 1,700 in size or so in this case. But even in this scenario, the probability of persistence to 50 is 21, to 500 is 1%. So this is somewhat concerning for this population in the lower Colorado River. And it seems we got about 10 or 11 years or so to right the ship for this fish. So the next question you might be asking yourself is, well, what results in good recruitment? You know, how can we guarantee fish back into the population? Well, if you recall, this graph has the recruitment strength on the y-axis and the year on the x-axis. You know, what makes these years that have 300, 400 fish versus these years in terms of the abiotic variables? Well, we can throw a slew or a suite of temperature and flow variables in a multiple stepwise regression model to figure this out. And so I included 36 temperature variables and 45 flow variables into this multiple stepwise regression process. And we come out with 4 variables that predict these strong years versus the weak ones. 2 temperature variables and 2 flow variables. And it accounts for quite a bit of the variation too. So this model did pretty well. So I'm going to present the results to you in what's called a principal components analysis. It's a way of graphing several variables in a 2-dimensional space. Okay, and I've set up each one of these cohorts. So like, for example, this one that's 428 in 2004 is this biggest bubble on the far right. Whereas that weakest year class that was recruited at 0 or expected to be 0 is the smallest bubble over there on your far left. Okay, on the x-axis, we account for 83% of the variation. That's the first principal component axis. On the second principal component axis, we account for 16% of the variation. So this first axis here, this x-axis, is one of our more important axes. And it's represented by September low flows and the high pulse frequency increasing in the positive direction, while September minimum temperatures are increasing in the negative direction. On the y-axis, a high pulse frequency and July minimum temperature increasing in the positive direction, September low flows increasing in the negative direction. Okay, so just follow the arrow out, whatever direction the arrow is going, whatever variables associated with that arrow, it's increasing in that direction. And so what this model is actually telling me, or telling us, is that whenever you have higher flows, higher pulse frequencies, and lower temperatures, you have a better chance of having a strong recruitment year. Because these 3 out here, our lowest estimated recruitment years, are represented by the highest September and July temperatures. So lower flows in the summer, hotter temperatures equal weak recruitment. Now, it did have high pulse frequency, right? But my assumption is that the temperature, the really hot temperatures in the summer kind of counteract that high pulse frequency. So wetter, cooler summers equal recruitment. And so in other systems throughout Texas and outside of Texas, they reported small or relatively infrequent capture of those small individuals. I told you we had very few young fish, right? But even then, they report between 5 and 15% of these fish within their capture. So, for example, some work that a colleague of mine was doing in the Sabine River, they captured 106 fish. We captured 200 in our study. But the thing I want to point out here first is that on the x-axis, you've got total length and a count on the y. So the number of individuals smaller than 500 within the Sabine River is like half the catch. Whereas within the Colorado River, I think it's represented by 2 individuals. So there are no young individuals within the lower Colorado River. And not only that, the sample size effort is pretty astounding. So I assisted with this work on the Sabine River. We captured those 106 individuals over the course of about 4.5 days. This was, in the Colorado, took us about 4 years. That's pretty astounding. And so I want to introduce this idea known as the extinction vortex. This was first introduced by Gilpin and Soule in 1986, and in it they state that there are multiple compounding factors that eventually lead to the extinction of a species. But I'm talking about a single population, so we're going to use extirpation instead. And what Gilpin and Soule are saying is that, let's say you've got a small starting population, and then some stochastic event happens. Well, that drought is going to end up resulting in weak recruitment. Weak recruitment will eventually lead to a smaller population. Smaller population results in a reduced genetic pool, which results in weak recruitment. And you get the idea. This kind of spins out of control, like the extirpation vortex. So in our particular case, we know that smaller populations are more susceptible to these demographic and environmental stochastic events. And in our case, we have commercial harvest of the species at one point in time, not anymore. But we know that it was happening in the lower Colorado River, at least anecdotally from fishermen reports. And we know that there was weak recruitment for the species or for the population from 2008 to present. Not only that, we have a really small starting population. Okay, so we're going to attempt to fill this in together throughout the next 2 objectives of this talk, okay? But first, we know that flow alterations are very likely a suspect in the recruitment. So take these 2 graphs here. Okay, you've got discharge on the y-axis on top and the count or frequency on the bottom one. And then it's graphed out by decade, so from 1900 to 2010. The decade recruitment are these 2 decades right here. Well, 1 decade represented by 2 bars here. And the frequency of these high pulse events is also drastically reduced in 2010 decade. And this is likely a product of the severe drought that Texas experienced from 2009 to 2015. And so the question becomes, how are they going to respond in the coming decade? Well, this has a lot. This will have a lot to do with whether or not there are any other factors to the recovery of the population. And I think a really good place to start is the habitat use and the migratory responses of the fish to certain flow variables, because we got to get them moving for spawning purposes, and we got to get them moving to the right spot. And so the question becomes, well, what is the right spot? What habitat are they selecting for? So we want to identify the habitat that they avoided as well as selected, determine if any substrates in particular can predict the use, and determine how substrate might affect the core area and the home range of the species. So the methods change a little bit. The area doesn't. We're still within the lower Colorado River, but now I've tagged fish at 5 locations of these big black dots here, relatively evenly spaced throughout the river. I went out and I surgically implanted these combined acoustic radio tags into the abdominal cavity of 42 bluesucker in December of 2014 and December 2015. I then went out on 38 relocation events to relocate these fish. So when I say relocate, I don't mean I pick the fish up and I put it in a new spot. I just went out and found it again. So every time I found it, it's considered a relocation. Over the course of the study, I ran about 12,000 river kilometers. It had an 84% relocation success rate. This resulted in 1,157 relocations. It's a pretty big data set we have here. But now we want to associate those relocations with habitat or substrate. So I also went out and ran the river with a side scan sonar unit. And we collected these raw sonar images and imported them into GIS. I then want to classify each area as a particular substrate type. So I went in by hand and created these polygons for all 290 kilometers. Yeah, as bedrock, boulder, cobble, gravel, sand, fine sediment, other, and submerged aquatic vegetation. The other category can include anthropogenic artifacts and trash. So now we can bring in the true relocations and draw a 5-meter buffer around them and intersect this with that substrate layer and get the substrate associated with each relocation. Additionally, we want to calculate the core area and the home range. And to do this, I used a tool called Fish Tracker in GIS. It's essentially a kernel density estimator. It restricts the analysis to the boundary of the river. And it does this assuming a constant swim. So it creates these predicted locations. For example, here's a raster image of the Colorado River. Here are true relocations of a fish. Okay, Fish Tracker is going to assume the fish was in these locations because it had to get from point A to point B somehow. And then from this, it calculates a 50th percentile kernel density estimate, which is the core area, and a 90th percentile KD, which is the home range. Okay, so we have the core area and the home range now. We also now import our substrate layer, right? And I can intersect this with the substrate layer and get substrate associated with core area and home range. And the last thing we want here is a linear core area and home range. So we just draw a straight line down the middle. You get the linear core area, linear home range. I just threw a bunch of stuff at you. Let's recap it real fast. We have the substrate associated with 1,157 relocations. We have the core area. We have the linear core area. We have the home range and the linear home range. Additionally, we have the substrate associated. Okay. So this first graph that you're going to look at here is going to have all of the available substrate throughout the river. So here it is in one single column. Okay. And what I want to point out from this is that those habitats or those substrates that are associated with blue sucker, at least that we think are associated with them, boulder, cobble, and bedrock, and sand, roughly 75%. And then the remaining 5 or 10% or so is made up by submerged vegetation, other, and environment. So the rest of the columns that are going to come in next are separated by season and year on the x-axis. And of course, on the y-axis is the percent occurrence, percent that they were selected for. And so here are the results of that. But what I want to point out specifically are that with the exception of the summer of 2016, the only substrates that are being selected for, as we might have predicted, were boulder, bedrock, and cobble, and sand, and occasionally the other category, which includes trash, were being actively avoided. Okay, so while this is interesting, this doesn't really tell us a whole lot that we didn't already know, but we can do some fun stuff with this now. So recall that Fish Tracker tool, right? It creates these predicted locations. I can take those predicted locations and put them into what's called optimized hotspot analysis. All right, so recall I told you that this tool assumes a constant swimming velocity. This becomes important because 1 and Fish 2, for example, both of them swam between point A and point B. Let's just assume the time frame was the same for both of them. Fish fills in the gaps with points, an equal number of points because the days in between relocation were the same. But Fish 2 is going to be weighted a little bit heavier in the analysis because the density of points, because the area is smaller, is a little higher. So now we have 177,000 plus points that we can put into the optimized hotspot analysis that can tell us where in the river fish are using more frequently. And so that's what you're looking at now. It's kind of a classic hotspot where your darker colors, orange and red, represent areas that were selected for. Greens are areas that were not selected for or avoided. So there are only 3 locations in the entire river. These 3 right here that make up about 55 river kilometers or 20% of the overall 290 kilometer study area that are being selected for. And that's around Bastrop, in between Bastrop and LaGrange, in that area surrounding LaGrange here. So this is kind of amazing considering how big the study area is actually. And not only that, the locations where we tagged fish were selected for because they were presumed to be spawning locations. So you would expect fish to be using them relatively frequently. So this tool also does something else kind of neat. It kicks out a z-score. So it ranks each of these hotspots between -3 and 3. So we can take this z-score, multiple stepwise regression analysis to determine if any of these substrates that I classified earlier are associated with these hotspots or the cold spots. The answer is yeah, actually. Boulder and cobble significantly predict these 3 locations. So what that means is that boulder and cobble more frequently occur within these areas than they do in other locations. And so this actually kind of got me thinking, right? The fish that were tagged in Bastrop had by far the smallest home ranges, both males and females. And so I got kind of curious thinking that it's possible that the substrate that's within their core area could potentially predict how far these fish would move throughout the entirety of the study, right? So what that has sand and submerged aquatic vegetation and artifacts and fine sediment, as that increases, you expect their home range to increase because they got to find that habitat that they're looking for, right? And then vice versa, as boulder, bedrock, cobble, maybe gravel increases, you would expect decreases. So again, a multiple stepwise regression analysis tells us that, yeah, actually, sand and trash and other artifacts that significantly predict how big the home range is going to be. So as sand and trash increases, the home range increases significantly. And not only that, it's like an order of magnitude greater, the home range that is. And so it seems pretty obvious to me that habitat is the limiting factor across the riverscape. Right here, you can see two blue suckers spawning behind, a boulder and this kind of like faster flowing water. And this is the area we would expect them to be. But again, only 55 river kilometers represent, this type of habitat throughout the entire 290 river kilometer stretch. And it determines how far a fish will move to find this particular habitat. And so I've already told you a couple of the effects of dam, right? That is, you have the loss of high magnitude flows, and you've seen this graph before. It's the same one from Austin. And the obvious implication is the fragmentation, right? So they lose some habitat, and they lose those high magnitude flows. Well, the issue with that is that high magnitude flows can alter the sediment load pretty significantly. And in fact, hydrology is known to be the keystone driver of habitat and substrate composition. Without, those big high flood events that kind of like reshape the river, it seems like they're not going to gain any habitat anytime soon. And so I think it's relatively safe to add limitations to our extirpation vortex. Okay, this leads me into the very last objective. This is the abiotic drivers of movement, which includes spawning. Right, so we're going to look at specifically at the end, but we want to look at movement patterns of the fish, the abiotic drivers of blue sucker spawning. Now, if and to what degree flow and temperature and habitat influences not only movements, but spawning migrations as well. And so to do this, the methods are exactly the same as the previous objective, okay? I had 5 tagging locations evenly spaced throughout the river. I went out and attempted to relocate them 38 times. But now we're interested in 3 very different variables. We want to look at displacement, which is directional, absolute movement, and then the spawning movement or the spawning migrations of the fish. And so what I'm going to show you next is a combination of like methods and results. It'll be a little bit clearer why I do that. It might be a little easier to understand. So this top graph is displacement, which I said was directional, recall. So anything in the negative direction is considered a downstream movement. Anything in the positive direction is considered an upstream movement. So for example, fish moves down 10 river kilometers in event 1, and then moves up 5 river kilometers in event 2. This has a displacement of 5 river kilometers. On this bottom graph here, now we have absolute movement. But assume the same, event 1, if the fish moves up 10 river kilometers, down 5 river kilometers in event 2. So this fish has an absolute movement of 15 river kilometers. So what I want to point out here from these graphs is that I've split out the movement patterns, displacement and absolute movement by year on the x-axis. And then each bar chart represents a season. So is winter. The most important thing to take away from this graph is that we're relatively certain that upstream migrations are occurring in the winter, right? But they occurred only in 2015 and 2016. In 2017, there were no migrations in the upstream direction. And not only that, in 2015, the magnitude at which they moved between 2015 and 2016 is not the same, right? So the absolute movement of 22 or so. And so this is a mean between relocations for all fish. So that is actually pretty significant. And the other thing to take note here is that in 2016, there was what seems to be an obvious migration upstream in the winter and a return in the spring, which is kind of what you'd expect for the fish. We don't see that same thing in 2017, or excuse me, in 2016. right? There seems to be some kind of delay. In the spring, there are essentially no migrations or no movements in the downstream direction in the spring. But in the summer, you see all those movements downstream. I think this has more to do with flow than anything. There was a pretty big flood event that kind of like homogenized flows across the river basin. But we'll explore some possibilities here in a little bit. The last thing I want to note in this graph is that in 2017, there's just not a whole lot in general going on. The absolute movement in that bottom right-hand corner there. So recall that riffle map that I showed you earlier, okay? We know that substrate is affecting the home range size. But the other thing I wanted to do now was turn those riffles into a hotspot, all right? So we're looking at riffle density. Anything red is a high density of riffles. Anything green is a low density. It seems that our highest density of riffles is around the Utley and Bastrop area. And it appeared that as riffle density decreased, that bluesucker were moving further. Right? I told you the fish were seeking out specific habitats, right? This might become, be kind of like an obvious conclusion for you. But I wanted to know if riffle density was an important metric in predicting, whether or not fish were going to make spawning migrations or not. But, what is a spawning migration? It's not necessarily an easy answer or an easy question to answer, because what I want you to note in these two graphs I'm showing you here, displacement on top, so directional on top, absolute movement on bottom, is that this top graph, there's nothing significant here, right? What that means is that fish ended up in more or less the same location where I originally tagged them. But, oh, right, okay, sorry. The x-axis is the tag number, but you don't necessarily need to know what each individual tag is. Just know that if these two are in line, it's the same fish. So this is like tag 50 or something. This is tag 73. So even though there's no significant difference in the directionality of these fish, there's a pretty big difference in the absolute movement, right? The tag 85, its absolute movement was 0. Its displacement, 0. Tag 46, displacement, essentially 0. But its absolute movement is like 40 kilometers between relocations. These two are not the same. They're not equal. And this bottom graph is what's known as a leptokurtic movement distribution, meaning that there are mobile and sessile individuals within the population. And those mobile individuals are really important. They're considered these genetic links within populations, right? So we need some kind of standard metric to determine what spawning migration is for, tag on your far right versus the tag on your far left. So this graph is here to point out one last kind of thing here about this leptokurtic movement distribution. This isn't just a product of where the fish. You might think that, if they're closer to that Bastrop area, they're all going to be sessile. Well, that's not entirely true. There are mobile individuals within each tagging location, right? So what I decided to do is use this temperature window that's from published literature, 10 and 23 degrees Celsius. So if a relocation event occurred within this window that I just stitched out, it doesn't count as a spawning migration. Okay, so this includes 18 of the months that I went out, of the 29 that I went out and attempted to relocate fish. That's step one of the spawning window. Step two is to determine, what percentile of absolute movement are we going to include, right? Because as I've noted, for example, tag 57 on the bottom left there has, some movements that in some cases that are 115 kilometers between relocations. Tag 41, and its greatest movement is around 9 kilometers. So I decided to just kind of standardize this and use the 85th percentile for the top % of data, which includes these movements. You'll see that maybe we might have missed a movement or two here or there, but anything inside of this, this stitched window, remember, doesn't count. So this results in 100 spawning movements, and those spawning movements receive a 1. Everything else receives a 0 now. And that's important because we're going to input it into a multiple logistic regression model with a subject effect. The other two dependent variables, displacement and absolute movement, are going to be a standard multiple regression model with a subject effect. So to account for temporal autocorrelation, I use an autoregressive covariance matrix structure, and then I took all these models and I ranked them in AICC. And I created 30 models a priori that could include some of these variables, right? That's maximum, mean, minimum flow between relocations, maximum, mean, minimum temperatures, as well as this change in riffle density between relocations. So this results in 90 total models, 30 for each dependent variable, recall. And I'm going to show you the top 5 of each of those dependent variables now. But don't try to read this, it's very busy. What we need to pay attention to are these highlighted areas. And even then, all I really want to point out is that absolute movement, displacement, and the probability of making a spawning migration all share something in common. They all have a flow variable, they all have a temperature variable, and they all have that percent change in rift density variable. And in terms of the absolute movement, which is kind of a pretty good metric for the maximum flow, mean flow, and the minimum flow all pop up in the model, indicating that every aspect of the hydrograph is important in this fish's life. But I want to focus in on, remember, the probability of making a spawning migration. We need to get these fish spawning. And so take a closer look at the beta variables, the beta estimates rather, of minimum flow, maximum temperature, and the percent riffle density to see what this model is really trying to tell us. So the beta estimate for riffle density is positive, and essentially what it's trying to say is that when a spawning movement is detected, there's a 30% increase in riffle density. It means they're making directed movements to these areas specifically for spawning. And interestingly enough, recall this optimized hotspot map. So I had an asterisk in this bass drop inset. And the reason that inset, or that asterisk is in that inset, is because this is the only location that was identified in both the optimized hotspot analysis for use as well as spawning locations. So when a spawning relocation was detected, it more often happened in bass drop than anywhere else throughout the river. So that area around bass drop is really important for this fish. In terms of the maximum flow, or excuse me, the minimum flow and the maximum temperature, both these variables, beta estimates, are negative. And so what it's saying is that, so what you're looking at is a hotspot, again, really. So red is the highest probability of making a spawning migration, blue is the lowest. What it's telling us is that as the maximum temperature between relocations decreases, you have a better chance of a spawning migration occurring. And it appears that around 13.8 to 17.8 or so degrees Celsius is our best chance. This is pretty amazing considering the range of temperatures throughout the entire river during the course of the study were between 5 and 38 degrees Celsius. So we've got it pretty honed in on temperature. It may not seem like we have it honed in on the flow because there's quite a bit happening along that y-axis, but even then it's between 8 and 65, 70 cubic meters per second. The range of variables during this study were between 2.5 and 2,600 cubic meters per second. So it's pretty good, actually. And the last thing that I want to present here is the probability of making a spawning migration by month, because this will become obvious why this is important here in just a moment. So the greatest probability of making a spawning migration was January, February, and March, regardless of year. Though February and March appear to be our greatest probabilities. And the reason that's important is because the Lower Colorado River Authority had a water management plan from 2010 that has flow requirements specifically for blue sucker. And in this plan, they mandated that flows stay at or above 500 cubic meters per second between March, April, and May, right? So I'm going to switch over to imperial units because the water management plan is written this way. So this 500 cubic feet per second is interesting because I think that the cue that's really missing here is the flood pulse prior to those low flows. I told you the predictor of a spawning migration occurring in terms of flows was right around 353 cubic feet per second. Those flows are on the descending leg of a big flood pulse. And on average, those flood pulses are around 7,000 cubic feet per second. And so I don't think that the homogenization of environmental flows, like mandating some kind of standard flow throughout the river, is necessarily the answer to queuing up spawning migrations. So I think it's relatively safe to add spawning miscues to our extirpation vortex. But recall that half the population is greater than 12 years old, right? That means the other half is between 3 and 11. They're in the reproductive prime. I don't think that we're necessarily here yet, but I do think that it's absolutely time to start the conversation about some potential conservation actions for this population. So some successful conservation actions that have occurred in other populations are captive propagation programs. So razorback sucker out in Arizona have recently been downgraded from endangered to threatened, and this is in large part due to the captive propagation program that they've implemented. The other potential option is habitat construction and burial removal. So habitat construction has shown quite a bit of success for Pacific salmon, but burial removal and habitat construction are also part of the reason that razorback sucker are no longer listed as endangered. Within our system, the Lower Colorado River, there is a small dam and a tributary known as Wilbarger. And that's significant because colleagues of mine have collected spawning blue sucker in that tributary, right? The last option here, constructing spawning habitat, is also another option. The location where that would be constructed is, is debatable, but it's definitely worth a conversation, I think. In terms of the future research actions for this fish, I think it's really critical we get a hold of the genetics, because here's the thing. It's possible that a bottlenecking event has either already occurred or is currently occurring, right? And that means that our effective population size, which I've estimated the population at 679, that's going to go down drastically if they're all individuals. And lastly, the tributaries. I mentioned how important I think these tributaries truly are, right? Colleagues have captured spawning blue sucker out in those tributaries, and it's possible there's a few isolated individuals. Recall that leptokurtic movement distribution that I presented to you earlier, where you had some sessile members of the population, right? It's possible that there are sessile members of those tributaries that don't necessarily use the main stem. And so I would like to end there, but first I want to thank all these people, specifically my committee members and anybody who spent time out on the Lower Colorado River with me, chasing these fish around. It's been a lot of fun. I'll take questions now. Thank you. Yes.
So how certain are you that your selection of this sample, that you were actually getting all age classes? In the fish literature, there's sometimes stage structured habitat.
Right. So I didn't mention it because I didn't really have time, but each one of the three habitats. So each one sample, in theory, we should have been able to capture young individuals that way. And I also did a staining protocol specifically. Not necessarily. There's a software program called the Indicators of Hydrologic Alteration. And basin by basin, it depends on what's considered a pulse and what's considered a flood. Within my system, I can't remember the cutoff, but there is a specific number that's broken up by percentiles. So it's like the top 10 percentile of the data is considered a flood pulse or a flood. And then there are things known as high flow pulses, which are below that threshold. In order, correct. Yeah. It could be an order of magnitude. It could also just be, it's broken up by percentiles. Yeah, Mark. I mean, it's really tough to say if that's the single thing, right? The analysis seems to say that there's a combination of flow and temperature at which recruitment is lowest, right? The really low flows, ultimately resulted in this this amazing growth of hydrilla and other in-stream aquatic vegetation, right? Which very possibly could have choked out oxygen. And there's a whole bunch of combinations of factors that could have led to the weak recruitment. But with the data we have available, that's our best predictor. Yes, sir. Yes.
Do you think the backdrop fires had any
That's a question I've never thought about. It's possible. It seems unlikely. So 90% of the contributing watershed is above Austin, right? So whatever fell out in Bastrop that ultimately ended up in the river, it was probably pretty minimal. It's probably flushed out by the flows that are controlled by the Longhorn Dam there in Austin. I doubt it had a big impact. Yeah, I doubt it. Yeah. Yes. I did. I also put out larval drift nets. Not blue sucker, no. We got other catastomids, but no blue sucker. unfortunately. Oh yeah, we looked for juveniles and larval fish, right? Like, they're just not there. Dr. Ball?
The lower the temperature, better for spawning. Right?
It seems that way, yeah.
Yeah. And then also, but then you also have the faster moving water with more water. Higher capacity. For the fire. How that may relate to temperatures at different times of year, how it may be a little more complex because of acidity. Does that make sense?
It does, and I think it is way more complex than, you know, kind of like standardizing these flows. I know it's easier for somebody managing a bunch of water and drinking water for 1 million plus people, but yeah, I definitely don't think it's the right option. So the reason that 500 cubic feet per second was selected was because there was a study prior to the one we completed here that that showed that they could maintain 80% of spawning habitat available to bluesucker. It had nothing to do with behavior or anything like that. It just, you know, how inundated is their habitat essentially, and that's, I don't think, necessarily the right question to be asking. Oh yeah, people are asking? Okay.
Segregated the population of the bluesucker on the Rio Grande from the other rivers.
It's segregated. So the question, what separates the populations throughout Texas, the bluesucker populations across Texas? So there was a genetic sampling done back in the, well, it was published in 1999 that separates the species. So the species, the population in the Rio Grande is the Rio Grande bluesucker, and then everything east of that is the, or within Texas at least, everything east of that is the bluesucker. How did I calculate cohort strength? That's not. The question was how I calculated cohort strength. Can you repeat that? I'm sorry.
Yeah, basically, I'm trying to figure out if there are any already gone extra Colorado might find by a river.
Are there any species that are extirpated from the river that you can find nearby? Well, there is this really strange population of spotted sucker in the South Llano River, which is a trib to the Colorado River. Why they don't occur throughout the main stem of the Colorado River, I don't know. I'm assuming it had to do with the fragmentation event. Probably why they're not there. Because everything above Austin is, you know, essentially a lake. I think so, yeah. Is that right, Heather? I think so.
Okay, thank y'all for coming. We're going to transition to the closed door section of this. 4, 5, 6 hours.
Great.